Hello everyone, my name is Michaela Rosenthal. I'm going to share with you the ecological pyrogenic components and management action for southern dry mesic oak forests of the upper Midwest within the United States. It's one of my favorite types of oak forests and a relatively unique one. Much of the Midwest is a mosaic of the prairie forest and savanna woodland transition zones. The focus of this presentation is on the upper Midwest states, specifically in southeastern Minnesota, northern Illinois and Indiana, southern Wisconsin, northeast Iowa, and much of lower Michigan. There's a need to emphasize the delineation of southern forests and northern forests. While the upper Midwest is a northerly region of the United States, forests are further distinguished based on regional weather, specifically the type of precipitation, so snowfall versus rainfall, how much, and average temperature. Northern forests are found in regions that are cooler and more moist. They tend to have a mix of broadleaf and coniferous species. Southern forests occur in warmer and drier regions, hosting broadleaf deciduous forests. Southern dry mesic oak forests occur on loamy soils of glacial till plains and moraines created from the glacier known as the Laurentide ice sheet during the Wisconsin glaciation. The erosional topography of the upper Midwest often has a loose cap. It's an accumulation of windblown sand and silt with very little clay, usually less than 20%. Canopy cover is defined as interrupted to continuous with 70 to 100% cover. Fire, wind throw, insect outbreaks, and pathogens associated with oak defoliation and decline are the prevalent natural disturbance factors influencing the establishment of these oak forests. Couple that with natural barriers such as rivers and topographic slope exposure, relatively prolonged periods of fire exclusion is likely the reason for closed or nearly closed canopy of these forests in the upper Midwest landscape. Southern dry mesic oak forests of today are mostly second growth forests, relatively young due to colonial deforestation and later fire suppression. Being second growth forests, the most mature trees range from 170 to 365 years old. The canopy layer is dominated by fire-resistant oak species, in particular white oak. On more mesic sites, red oak can be codominant, and to a lesser degree, bur oak. Hickory species, including shagbark hickory, bitternut hickory, and mockernut hickory, are diagnostic in proportion of the range of this forest type. Depending on the site location and overstory canopy density, the woody understory may include species such as juneberry, chokeberry, American hazelnut, and maple leaf viburnum. In fire-suppressed systems, mesophytic shrubs and trees such as maple and basswood are becoming dominant in the subcanopy and even succeeding into the canopy layer. This phenomenon is known as mesification. Intact, healthy, dry mesic oak forests have a plethora of ground layer herbs. Pennsylvania sedge, pointed leaf tick trefoil, wild sarsaparilla, and several ephemeral species such as great white trillium make up the dominant herbaceous ground layer. The now extinct passenger pigeon was likely a keystone species in development of oak ecosystems, roosting in oak forests by the thousands. Today, southern dry mesic oak forests support a variety of animal species, including southern flying squirrels, various flycatchers, ovenbirds, wood thrush, wood frogs, and the little brown bat. Oak species within these forests are notable for a number of traits that appear to be adaptations to fire, such as thick bark, vigorous sprouting ability, and flammable leaf litter that facilitates fire spread. Within these forest types, American hazelnut also readily resprouts from fire. Nitrogen-fixing plants like that of pointed leaf tick trefoil play an important role in replacing nitrogen lost from soil and fire-dominated ecosystems. Studies show that both cover and frequency of nitrogen-fixing plant species are higher on burned sites, while ephemeral plants like shooting star and great white trillium emergence is seemingly timed for mid to late spring after historic dominant season fires that clear away detritus and oak leaf debris. There's little direct evidence to confirm how animal species respond to fire within southern dry mesic oak forests, Yet animals like flying squirrel and woodpeckers construct or occupy nest cavities within tree trunks and can find suitable shelter from fires. Fire also hollows out dead heartwood, especially in red oaks, contributing to this potential habitat, while ground-dwelling animals like the wood frog have been observed to find microrefugia, often noted as behavioral and physiological adaptations to maintain water balance during and after wildfire. Southern dry mesic oak forests would have historically occurred near natural fire breaks, such as along eastern edges of stream corridors, along peninsulas and lakes, adjacent to wetlands, and on broken topography typical of end moraines and ice contact cams. These natural barriers have great influence on fire. Yet, according to multiple studies, from 2000 to 5,700 years before present, fire was a natural disturbance within these oak forests. Abrams et al. Found that only 50% of the fire frequency data dates within the region were associated with significantly dry years. Pollen studies conducted within the upper Midwest region have also found that the presence of oaks is often associated with deposits of charcoal, indicating that presence of oak expansion were often correlated with reoccurring dormant season fires. Dormant season fires have been confidently attributed to indigenous ignitions, whereas growing season fires could be either natural or indigenous. Even though understanding of indigenous fire may be underrepresented in many studies due to knowledge lost from diminishing populations since Euro-American colonization, comparing dormant to growing season burns within southern dry mesic oak forests serves as a way to estimate the importance and persistence of indigenous ignitions relative to natural ignitions. Without constant indigenous fire presence, southern dry mesic oak forests would likely have never existed due to natural barriers. Historically, southern dry mesic oak forests experienced low severity fires replacing less than 25% of the upper canopy layer, with a fire return interval spanning no more than 35 years. Mixed severity fires have occurred in southern dry mesic oak forests. They tended to replace up to 75% of the upper canopy layer. According to one fire scar analysis, the average fire return interval was 4 to 16 years within oak forests of the upper Midwest. Much like land use change during Euro-American settlement in the upper Midwest, the fire vegetation relationship has changed over the past 400 plus years due to extermination of indigenous peoples and suppression of fire as a cultural science practice. Fire return intervals within southern dry mesic oak forests have decreased to several hundred years. Figure 3, found on the slide, was taken from a study of historic context to Euro-American settlement era fires of the Lake States. It shows a fire chronology for sites within Wisconsin. Settlement era fires were less frequent than pre-settlement fires, with little evidence that slash from tree harvesting impacted fire frequency or occurrence at site or ecoregion scales. Settlement fires also tended to burn during significantly dry periods, the same conditions driving large fires within the upper Midwest. For better or worse, the lack of fire within the upper Midwest landscape has set the stage for future management. While there is increasing commingling of human development within wildland vegetation, the risk of wildfires is less of a concern than smoke management and the general public's fear of fire within forests. This fear perception could drive future fire suppression decisions in present-day fire-managed southern dry mesic oak forests. Despite a warming world that should promote warm-adapted fire-tolerant genera, such as oak, hickory, and grassland communities, the increased invasion by cool-adapted, fire-sensitive mesophytic trees like maple, elm, and basswood have occurred due to the absence of burning. The leaf litter of these replacement species is less flammable and more rapidly mineralized than that of the oaks, reinforcing mesification. Non-native invasive species of the upper Midwest also contribute to community transition. By altering the composition and structure of southern dry mesic oak forests, they are now retaining moisture, filling gaps, and shading out understory vegetation, and nutrifying the soil, reinforcing this positive feedback phenomenon. The trend towards increases in non-oak tree species will continue in fire-suppressed oak forests, rendering them less combustible for present and future forest managers who wish to restore natural fire regimes. Increased deer density beyond historic levels and the growing number of insect and pathogen outbreaks like spongy moth and oak wilt are compounding factors that must also be addressed if there's a desire to sustain southern dry mesic oak forests into the future. While there is potential for a post-mesification era to occur with a warmer climate, the magnitude reversal will depend on the extent to which the other factors mentioned continue to work against oak. Southern dry mesic oak forests on very dry sites should be relatively easy to manage through fire for sustained oak regeneration. In general, it may be easier to create or maintain oak dominance on south and west-facing slopes. In the younger and more nutrient-rich glaciated soils of southern Michigan and southeastern Wisconsin, management strategies should be centered on prescribed burning, understory removal of competitive species and non-native shrubs, and control of deer browse as well as insect and pathogen outbreaks. Current and future management efforts should focus on release and recruitment of understory oaks relative to competing species using a variety of strategies sustained long term. One study concluded that at least 1,063 stems greater than 4.5 feet in height of oak saplings advanced regeneration per hectare prior to a clear-cut harvest. The clear-cut forest ultimately produced a pole stand containing 30% oak. Shelterwood harvests have been and should be utilized as an alternative to clear-cutting on more productive sites. With a shelterwood cut, residual oak trees are left in the overstory to moderate the understory microclimate, provide regenerative seed mass, and to allow for enough shade to discourage shade-intolerant species growth. That said, gap size matters. Smaller gaps between 20 and 100 meters square formed in southern dry mesic oak forests may slightly increase growth of overstory oaks and hickories or accelerate growth of understory maple species. Conversely, gaps exceeding 400 square meters may stimulate recruitment of understory oak species and maples, ash, aspen, cherry, and sassafras. All in all, only when canopy gaps are sufficiently large enough with canopy cover ranging from 25 to 50% are oaks able to take advantage of their high photosynthesis to respiration rate ratio and recruit quickly into the overstory. Timing of shelterwood cuts should coincide with acorn crops. The success of prescribed burns in conjunction with these other management strategies in promoting oak regeneration is highly dependent on local ecosystem characteristics. In other words, the initial condition of the southern dry mesic oak forest prior to disturbance largely determines the outcome of post-treatment success, be it clear cutting, targeted release, and/or fire. Removing the duff layer can provide a 1 to 2 year window of opportunity for oak seedlings to germinate, and especially if the fire is timed to match a mast year for acorn production. Understory stems greater than 4 centimeters DBH of fire-sensitive species are robust enough to survive low to medium intensity fires, so follow-up release is needed. Prevention of insect and pathogen outbreaks is best approached by maintaining low stem density, which, as described previously, is both conducive to oak regeneration and inhibition to density-dependent spread of infections. O'Brien et al. Suggested forest stands with low overstory density and high overstory diversity may slow down the spread of oak wilt. Thank you. The following 2 slides include the references used for the creation of this presentation.